The Delhi iron pillar has survived because it rusted, not because rust somehow missed it. Its makers didn't forge chemically perfect iron, and they certainly didn't possess some impossible metal. For roughly 16 centuries, corrosion has attacked this pillar outdoors, and that attack created a microscopic shield, then slowed itself almost to a standstill. Phosphate, fed by an impurity modern steelmakers usually try to remove, makes up part of that shield. The famous rustless pillar is covered in rust, but it's the right rust, on the right iron, under the right sky. Inside Delhi's QTB complex stands a pillar rising more than 7 meters and weighing over 6 tons. Its Sanskrit inscription praises a ruler called Chandra, and most scholars identify him as Gupta Emperor Chandragupta II, placing the pillar around the late 4th or early 5th century. Some researchers propose Udayagiri, hundreds of kilometers south of Delhi, while others remain unconvinced, since the inscription never supplies a modern address. Here's what the monument proves without controversy. Gupta-era ironworkers coordinated labor, fuel, furnaces, and forging on an extraordinary scale, creating a towering iron standard long before industrial foundries existed. And they did it without pouring 6 tons of molten iron into a mold. That's the first lost-looking technology. But making enough iron was only the beginning. The next challenge was joining that iron into one body. Ancient bloomery furnaces produced relatively small, spongy masses called blooms, each one containing iron, unreduced ore, pores, and trapped slag. Smiths reheated those pieces, hammered them, and forge welded them together, repeating that cycle until separate masses became one colossal shaft. Hundreds of furnace heats may have supplied the required metal, according to one reconstruction, though the exact workshop sequence remains uncertain. You can't dismantle a protected monument to inspect every internal joint. Radiography, ultrasonics, and surface metallography reveal elongated voids in a forged structure, and those clues support construction through repeated welding and radial hammering. Picture that scene for a moment. Teams controlled heat by sight, moved glowing iron, and struck coordinated blows, and a failed weld could have weakened years of work. Instead, their uneven material endured transport, erection, impacts, monsoons, and centuries of exposure. Modern metallurgy often treats pores, slag, and chemical variation as defects. But inside this pillar, some of those defects helped create its armor. Those supposed defects change how the pillar begins to corrode. Its wrought iron contains very little carbon, but unusually high phosphorus, though measurements vary since the metal isn't uniform. Reported phosphorus values range roughly from 0.11 to 0.48%, with an often cited average around 0.25%, and many modern structural steels contain far less. Steelmakers usually restrict phosphorus because too much can reduce toughness, but the ancient smelting route didn't prioritize removing it. Its solid-state process also left slag particles scattered through the iron. At first, those inclusions can accelerate tiny electrochemical reactions, which sounds disastrous. Corrosion begins, iron dissolves, and rust products gather across the surface. Here's where it gets interesting though. Phosphorus becomes concentrated near the boundary between metal and rust, and the attack starts changing its own conditions. Rather than producing only loose, porous scale, the surface starts building something denser. This is where ordinary rust becomes a defensive system. That defensive system forms in stages. First come familiar iron oxides and hydrated oxides, and then phosphorus promotes a compact amorphous layer of delta iron oxide hydroxide, a phase researchers often call misawite, written chemically as delta-FeOOH. It hugs the metal more tightly than flaky red rust, restricting the movement of water, oxygen, and ions toward fresh iron. A second barrier then develops at the metal-rust interface, containing crystalline hydrogen phosphate hydride. That name sounds obscure, but its job is simple. Low porosity makes the route toward the underlying metal increasingly difficult. The pillar never becomes immune. Instead, each new corrosion reaction faces a slower journey through an aging shield. IIT Kanpur metallurgist R. Balasubramaniam reconstructed this process from rust examined with X-ray diffraction, infrared spectroscopy, and Musbauer spectroscopy. Together, those methods detected phosphates, several oxyhydroxides, and magnetite within the complex scale, and his model identified the crystalline phosphate at the metal-rust interface as the critical long-term barrier. But a strong explanation isn't a finished mystery. In 2009, U2009, Upanid Mystery, Kamachi Mudali and Boldev Raj took electrochemical measurements directly on the pillar and confirmed that its age scale behaves passively, though this protection is heterogeneous. Its behavior varies by location, and the scale near the top showed stronger passivation. Protected status limits direct sampling of the metal beneath it, so the phosphate-centered mechanism is well supported, but its exact kinetics, local variation, and atomic scale development remain active questions. Even perfect chemistry would fail without a second partner, and that partner isn't another element. It's time spent alternately wet and dry. Rain and humidity provide moisture for corrosion reactions, while dry intervals help phosphate-rich products mature and crystallize. Repeated cycling favors a dense, adherent barrier instead of permanently soaked rust, which means Delhi's atmosphere helped the pillar's unusual iron protect itself. The material and environment work together, and neither explanation is sufficient alone. Put ordinary iron under those conditions and it still corrodes much faster. Remove the drying interval and the cycle that matures the phosphate barrier gets disrupted. We know the protection has environmental limits because the buried portion didn't remain pristine. Researchers reported a rust layer about 1 centimeter thick and deep pitting below ground, while the exposed scale, by comparison, varies from tens to hundreds of micrometers thick. So rust-proof is the wrong word. The pillar resists destructive atmospheric corrosion under favorable cycles, but change those conditions, and the miracle immediately acquires limits. Those limits dismantle the mythology without diminishing the achievement. There's no evidence for an invisible coating, secret butter treatment, or impossible alloy, and certainly no need for ancient aliens. The surviving evidence points toward bloomery iron, forge welding, phosphorus, slag, and climate. Could modern industry reproduce that recipe? Yes, in broad chemical and metallurgical terms. Researchers can manufacture phosphoric iron and study its corrosion. And what nobody can accelerate is a 16th century field test. The pillar also carries its own irregular microstructure and unique exposure history, so unreplicated needs careful handling. We haven't duplicated this exact monument and watched it survive another 16 centuries, but that's different from saying its material is beyond modern science. We also can't prove its smiths understood phosphate chemistry. They may have selected ores and processes through accumulated workshop experience, knowledge that could have been empirical, transmitted through practice rather than formulas. The real loss may not be a secret ingredient. It may be the human system that reliably organized thousands of difficult decisions. So what remains when that system disappears? Evidence remains, and new instruments keep teaching us how to read it. In 2021, a scientific reports team led by Deepak Trivedi examined iron preserved from the Agaria metallurgical tradition in central India, material that wasn't sampled from the Delhi pillar itself, and that distinction matters. Using microscopy, spectroscopy, and neutron imaging, the team showed that hot hammering changed the material's pores and corrosion film. Within the limits of their instruments, they didn't detect phosphorus in the iron itself, but they found it in slag and identified other slag-associated elements in the protective scale. That doesn't disprove the pillar's phosphate-centered mechanism. It shows that traditional corrosion-resistant iron didn't necessarily follow one universal recipe. The study supports forging and microstructure as important variables, but it doesn't prove airy Seth. Inspections of the pillar reveal a more urgent lesson. Its scale is heterogeneous, and damaged areas can corrode differently. In 2010, Achal Pandya and D.D.N. Singh reported fast-growing yellow corrosion around an area damaged by an 18th century cannonball impact, then reproduced a similar dent in iron with a comparable composition. Electrochemical tests supported a disturbing result. That metal under tensile stress corroded preferentially when the environment reached it. The monument still needs monitoring and conservation. Its survival isn't the completed event. It's an experiment still running in Delhi, and that experiment changes what advanced technology can mean. The pillar's deepest lesson isn't that ancient people knew chemistry, modern people forgot. It's that technology can exist without modern scientific language. Skilled workers combined ore, charcoal, heat, timing, hammering, and collective judgment, and their process left phosphorus and slag inside the iron. Delhi's wet-dry rhythm then transformed those remnants into protection. An apparent impurity became useful. An apparent failure, rust, became a shield. and an apparent mystery became evidence of disciplined human craft. None of that knowledge was supernatural. It was material, environmental, and deeply social, which makes its partial loss more human and more important. Craft and environment kept working after its makers vanished, and that's why the Delhi pillar survived. Subscribe for the next lost technology, where archaeology meets the science hidden inside surviving objects. The next artifact may preserve its maker's answer in metal, stone, or glass.